right? And can actually be observed in people's written comments about the way they make choices in games, suddenly not only gets us, in this case, any prediction at all, but actually a pretty good prediction about what people will do under different circumstances. Right? General rule of the class. Of course, the stuff I've shown you has been carefully selected to work well, so it doesn't always mean that introducing one element of psychological realism to an otherwise rational model will get you better predictions, but it's just another demonstration of the general lesson we want to convey about the quality of predictions and how we can improve the quality of predictions by introducing some psychological realism. Okay, now here's testing a level K model, and what would be wonderful would be if we could test the level K model against all other possible alternatives. We're not going to be able to do that. We're going to test it against one other seemingly quite compelling alternative, just to get a sense of how, well, actually two, because we're also going to test it against Nash equilibrium, just to see how you could conduct such a test. And the most important thing, sorry, I'll get to the most important thing after I tell you the second most important thing. So let me just introduce this alternative model that we're going to test level K against, which is the dominance thinking model. Okay? So dominance thinking is an alternative model of bounded rationality. We feel relatively confident that bounded rationality is a meaningful concept to explore. It doesn't necessarily mean that the level K model of bounded rationality is the right one. Okay, so we're going to look at a model that is based on the idea of iterative deletion of dominated strategies, which is, in many cases, a fairly psychologically compelling kind of thing to imagine people actually do. And then look at what happens if we incorporate that into a model of bounded rationality. Okay? So I'm going to repeatedly call iterative deletion of dominated strategies IDDS, otherwise my slides get ugly. So it works like this. You have different steps, similar to the different levels. A step 0 dominance thinker does this. They simply assume that all other players play uniformly across the range of possible actions, right? Which is to say they assume that other players do 0 rounds of deletion of dominated strategies. They just don't think about it. Okay, so this is the same exactly as a level 1 thinker in the level K model. Okay? In the beauty contest, with a P of 2/3, a step 0 would think everybody else is choosing randomly, which means their average would be 50. I'll guess 2/3 of that, 33 1/3. Exactly the same result as for a level 1 thinker, level 1 player. What does a step 1 dominance thinker do? Now, in the level K model, each level bases their assumptions of what the other players will do on a sort of slightly dumbed down version of what they themselves are doing. Right? This is going to be different than that, and I think in some sense a stronger assumption. Here, we'll have a step 1 player assume that other players play uniformly after one round of iterative deletion of dominated strategies. Right? So what's noteworthy, and then they'll respond optimally to that. So what's noteworthy is that a step 1 player is not engaging in any rounds of iterative deletion of dominated strategies. That's not their strategy. They're assuming that other people do that strategy and then do something even dumber, which is to choose randomly over the remaining interval, and then I'm going to do the smart thing. Right? So it's not just that other people are one step less sophisticated than me, but that I actually think they're behaving in a completely different way than me. Okay? So I think a little bit stronger assumption in some sense. But basically what that would do in the beauty contest, step 1 assumes that others have eliminated everything above 66 2/3 and then chosen randomly over the remaining interval from 0 to 66 2/3. So they will think, a step 1 thinker will think that the average of other players is 33 1/3, and we'll multiply that by 2/3, and they'll guess 22 points. It's actually 22 2/9. Exactly the same as a level 2 player, right? And it goes on from there, right? So at step 2, we'll guess 14.4, which is also exactly the same as a level 3 player. Now, on the one hand, it's like, oh, that's pretty cool. This model works too. On the other hand, it's not doing as much good in terms of the scientific process, because when two models make the same predictions over a data set, you can't use that data set to distinguish the models, right? Obviously. So what you have to do in the scientific process is you come up with a bunch of models that can explain the data you've already got. Then you've got to come up with some experiment or some other data set that you could get your hands on in which the models make different predictions. And then you look at that data, you can tell which model is more correct. So this is exactly what Costa, Gomez, and Crawford did. I'm pretty sure this is the assigned paper. They got a bunch of papers. And not much of this paper is assigned because not much of it is really particularly intelligible. But so it's a short read. But here's what they did. They concocted, very similar to what Charnas and Rabin did in trying to tease apart different social preferences, they concocted an experimental setting that would, where these two different models would have different predictions. Okay? So they have a two-player simultaneous moves guessing game, similar to the beauty contest. And I'm sorry, the word guessing here is not quite right, because people aren't guessing. They're submitting an answer that we're going to call a guess, just so we've got a useful word, an easy word to use. It's not, presumably it's not a total guess, it's an educated guess, let's say. So each player is randomly assigned different ranges. I don't know if they made the rule that in each two-player set they had to have different ranges, or maybe sometimes they had the same range, I'm not sure. But each player randomly is assigned one of these 4 ranges, and then one of these 4 targets. And a target is an unfortunate term here. I would have called it something else like a multiplier. Okay, so you get a target and you get a multiplier, and then, sorry, you get a range and a multiplier. And then your goal, your payoffs are based on how close your guess is to your opponent's guess multiplied by their target, multiplied by your own target. Right? So if I'm player 1, well, I'll show you an example on the next slide, but the idea is that your goal is to try to figure out what your opponent is going to guess, and then multiply that by your multiplier, and your guess should be that. No. That your goal, the payoff is just based on how close you get to your goal. Your goal is to figure out what your opponent's guess will be, and then multiply it by your multiplier, and guess that. And then if you hit the spot, you get a big prize, and if you're a little bit off, your prize goes down. I'm guessing they probably use the quadratic scoring rule, which we haven't looked at, but it's a complicated incentive compatible experimental rule that people put a lot of faith in. Okay, both players have complete information. They know each other's range and target. Okay, now they don't really have complete information because they don't know the other person's level of bounded rationality or what model their decision-making process follows, but they know the other person's incentives and choice set. Okay, and then they each subject played 6 games in which they randomly varied 16 games. Sorry, the ranges, the targets, and the opponents. Okay, so in some sense, what they were going after was a situation where they have a whole bunch of data of people not playing the same game over and over again, but each game slightly different opponent, different range, different target, so people wouldn't fall into a rut. And it turns out that this game, that the predictions of what people should do in this game are radically different under the 3 competing models that we'll look at, the Nash equilibrium, and the level K, and the dominance thinking. I'm not going to go into solving the Nash equilibrium because it's a pain in the neck and it's not what I think is most interesting here, nor is it the kind of thing I'm likely to test you on. So what I want to do is sort of work through how we would figure out the predictions of these 2 models of bounded rationality. Okay, so to figure out the predictions of the dominance thinking model, we have to begin by figuring out what iterative deletion of dominated strategies would look like. I think I'm going to do this on the screen. Okay, So let's just suppose that player 1 gets this range of 100 to 900, player 2 gets a range of 100 to 500, and these are their target, they're multipliers, they're targets. Okay? In round 1 of iterative deletion of dominated strategies, what does player 2 do? 2 will go somewhere between 1.5 times 100 and 1.5 times 900. Yeah? This is a perfectly rational player. We're just simply going to put bounds on what they could conceivably guess. Right? In other words, what will they rule out? What can we rule out? Okay, player 2 is taking their multiplier, which is 1.5, and multiplying it by player 1's guess, which has to be between 100 and 900. So player 2's guess will be in a range that is where the endpoints are defined by taking player 2's multiplier and multiplying it by the endpoints of player 1's range. Okay? They're not allowed to guess above their range. So here's what happens, right? So what happens is, so this is 150, this is 1350, but they can't go above 500. Okay? So their range becomes 150 to 500. Right? So anything below 150 is strictly dominated by anything above 150. Okay? So that's one round of iterative deletion of dominated strategy for player 2. Player 1 will go somewhere in a range defined by 0.5 times 100 and 0.5 times 500. Right? So that's 50, and that's 250. And of course, they can't go below 100. So their range becomes 100 to 250. Right? And anything above 250 is strictly dominated by anything below 250. Okay? I think what I'll do to just save time is to not work through the details of IDDS for round 2, but just tell you that if you go through the same process with these new ranges, a second round of iterative deletion of dominated strategies would wind you up with a range for player 2 of their range would go 150 to 375, and player 1's range would wind up actually not changing. It would still go from 100 to 250. And you can keep going. Okay, so then if we take those, so those are sort of like the building block. Right? In level K, the building block is what is a level 0 doing, and then you go from there. In dominance thinking, the building block is what would rational iterative deletion of dominated strategies look like, and then we can build on that. Okay? So step 0 player, right, believes that other people are just choosing randomly over the original intervals. And so they think that the relevant ranges are these. Step 1 player believes that the relevant ranges are those, which we generated after one round of IDDS. And step 2 thinks they're these, and so forth. Okay, we'll stop at 2 just because eternity is not now. Time is short. All right, so what will step 0 player do? Well, player 1, what were their targets again? So target 1 was 0.5, is that right? And target 2 was 1.5? Is that right? Yes, that's right. Okay, so player 1 says, all right, player 2 is going to choose somewhere in there, and the average of 100 and 500 is 300, so I'm going to go 150. Player 2 is going to think the same thing between 100 and 900. The average is 500, and I'm going to multiply that by 1.5, and I'm going to get 750. Step 1 players are not going to think about what a step 0 player would do. They're going to think about what a player would do who had done one round of iterative deletion of dominated strategies. Right? So player 1 is going to say, oh, player 2 is going to go between 150 and 500, and the average of that is something which, when you multiply by 0.5, equals 162.5, and vice versa for player 2. Boom. Yeah. Yes. Oh, eraser, please. Okay. Step 0. Player 1, and a lot of this, by the way, a lot of what's complicated about this isn't the complication of the model, it's the complication of this specific game. Okay? This specific game is kind of irritating to solve. Player 1 says, okay, a completely naive player 2 who was playing randomly in the range between 100 and 500 would, on average, guess 300, right, which is the average of 100 and 500. So I'm going to take 300, I'm going to take 300 and I'm going to multiply by my target, which is 0.5, which is 150. Okay? And player 2 is doing the same thing, saying I think player 1 will choose randomly in this range 100 and 900, average is 400 and 500. I'll multiply that by my target, come up with 750. And basically, steps above that are doing exactly the same logical exercise on a different set, with a different assumption about what set of trimmed ranges their opponent is randomly guessing from. Okay? Now, if this model was correct, if this is actually the cognitive process that people go through, I would be inclined not to conclude that people actually believe that other people are choosing their guesses this way, but simply that forced to come up with some framework for thinking strategically about what other people might do, this is the best that folks can come up with. Right? If it were the true model, that would be how I would be inclined to interpret it. Okay? I'm not thinking that the best I believe my opponent can come up with is one round of iterative deletion of dominated strategies and then guess randomly. It's actually the best I can come up with. So that's what I'm going to apply. Which, by the way, is exactly what standard economists have been doing for the last 120 years. Right? I don't actually think that what people do is to discount all future periods by a constant exponential discount factor. I don't actually think that that's the best people can come up with in making their decisions about intertemporal trade-offs. It happens to be the best I can come up with as an economic mathematician, so I'm going to roll with it. Because if I try to get closer to the truth, my head's going to explode. Okay, and step 2 does the same thing. Right? Step 2 applies their target to their opponent's range after 2 rounds of iterative deletion of dominated strategies. And the point is that these predictions are... Oh, whoops, no, I haven't got to the point yet. Okay, so those are the predictions for the dominance thinking model. What about the level K model? Okay? So recall, the point here is that each player thinks the other does one fewer rounds of reasoning. What would a level 0 player do? We don't have the ranges on the board anymore. But player 1, a level 0 player 1, just chooses randomly from their range, which is 100 to 900, with absolutely no reference to the other player's range. And player 2 chooses randomly from their range, 100 to 500. Okay? So there they are. And then, for the remaining levels above that, we can forget about the ranges completely. Because they don't care about the ranges anymore. They just care about what an opponent with one less level of sophistication would do. And we already have that. So we've done all of the work already. Player 1, a level 1 player 1 just takes a level 0 player 2's number and divides it in half because their target is 0.5. And a level 1 player 2 just takes player 1's level 0 guess, which is 500, multiplies it by 1.5, which gets us 750, but then it's truncated because player 2 can't go above 500. Okay? And you can just apply the same logic up for levels. Each level best responding to what the level below them would do. Okay? And the point is that these, right, so this corresponds, sorry, that corresponds to nothing. This corresponds to a step 0 player in the dominance thinking model, and this to a step 1, and this to a step 2, in terms of the level of sophistication, right? But the predictions are totally different. That's the point of this game, is that they cleverly devised a game where a step 0 player does not play the same thing, as a level 1 player. Actually, a level 1 player 1 does play the same as a step 0 player 1. All of the other predictions are different. Okay? Now we just crank up the game, see what the results tell us. Okay? And it turns out, just to cut to the chase and not present you with a lot of tables, that the majority of subjects, and I'm sorry I don't know the exact number, but it's in the paper, guessed within 0.5, which is to say very close, to one of the level K types guesses. Okay? So some distribution of guesses, but the majority of guesses were spot on for some level of the level K model in at least half of the games they played. So a majority of subjects played some level K spot on at least half the games. Now, maybe they just got tired in the other games. Maybe it took them half the time, the first 8 games to figure out even a level K model. We don't know. But this is actually relatively compelling as lab results go. So there were a few dominance thinkers and even a few equilibrium players, and some subjects hard to categorize. I've already sort of groused to you about the phenomenon of jaded professional subjects who just go in and they say, I'm not here to participate in science, I'm here to get $15. So they just do silly things. Don't do that. It's actually a violation of student code of conduct. There's a place in the student code of conduct that says that you must not knowingly do anything to undermine academic research. And blowing off your, just not following the instructions and just guessing randomly when you're part of a student subject pool is a violation of that part of the student code of conduct. Okay. The authors went one step further and studied how subjects came up with their guesses. Now, we've seen in the beauty contest how we can just ask people how they came up with their guesses and get answers that are pretty compelling and seem to point us pretty directly towards the level K model. These guys took this a step further and used a tool that you can actually use in lots of other settings. What they did was they created a screen in which they presented to each player, here's your limits and targets. Here's your lower limit, here's your target, here's your upper limit, and your opponent's limits and targets, but they were all blank. And costlessly, players could click on the different boxes to reveal the particular pieces of information hidden behind them. Right? So it's not like they had to pay a fee. We're not interested in people's willingness to pay for assistance with solving the problem. They can't solve the problem without the information. They have to click some of these boxes in order to make any kind of guess. They can only click one at a time. The order in which they click them should tell us something, in most cases, about, unless they just say, give me all the information, right? The order in which they click them should tell us something about the order in which they go through their cognitive process. Okay? So for example, consider what a level 2 level K player 1 would need to look at in order to generate her guess, right? So first she has to figure out what a level 1 player 2 would do. And so a level 1 player 2 responds to a random player 1. So a level 1 player 2 needs to know what player 1's range is, right? First they would have to look up, first they have to look up their own limits to know what a level 1 player 2 would do. And then they have to look up player 2's target to know how player 2 would respond to that. Okay? And then they would have to check player 2's limits to make sure that range wasn't truncated in some way. And then they would have to look up their own target in order to their own multiplier in order to decide their own guess. And so you can specify precisely the order in which people would need information in order to complete the steps of either of these different models. And what they found was that the order in which subjects look up information corresponds very closely to the level K type that their answers put them in. Right? So maybe not a very surprising result. If your answers are within 0.5, right? These ranges are over several hundred. Your answers are within 0.5 of the prediction of a level 2 player. The fact that you revealed information in precisely the order the level 2 player would need in order to reach the level 2 prediction shouldn't be that surprising. It is, however, great science, and it's very convincing. Okay. So that's a little bit of talk about the scientific process, and hopefully enough talk about these two models for you to be able to solve problems using either of them. Okay. Last topic. Can irrationality survive amidst rationality, which is sort of moving us in the direction of one of the bigger questions of the field of behavioral economics, which is, does market competition or any other kind of competition or just in general the rigors of the real world squash the impact of rationality and somehow either force irrational agents out or discipline them so that they have to behave rationally? Now we've seen with social preferences, which by the way, we're not claiming is a case of irrationality per se, but non-standard, non-purely self-interested preferences do, at least in the laboratory, seem to get squeezed out under competition. And people wind up being sort of forced by competition to play what look like perfectly self-interested strategies. Okay? We've also seen that in labor markets, that's not necessarily true, right? Or at least in experimental labor markets. So let's look at some, oh dear, I didn't put in any, I wanted this to reveal itself in little steps. This is a bit of a mess. So let's look at what we can conclude by looking at some behavioral game theory. So consider a beauty contest with 10 players and winning at 0.95 wide. That's to say, in this case, p is not 2/3, but is 0.95. Okay? You get the same kind of result qualitatively for any value of p, but this just exaggerates the results in a way that should be suspicious to you, but I'm just trying to inflate the results so they're more striking, like any good scientist should. Sorry, don't take that seriously. Let's suppose that 9 of these 10 players are perfectly rational, unboundedly rational, and purely self-interested, and that one player is irrational in the sense that the irrational player always guesses 50 on average. So basically, they just choose randomly between 0 and 100. Okay? And we'll also assume that the R's, in addition to being unboundedly rational, also have rational expectations, so they know that the irrational guesses that way.